Last talk of today, the first day of the conference, is Sarah Tavella, who will be talking about pushing down solar radial velocity precision to 50 centimeters a second. I'm just going to full screen this, I think, because it's a PDF. Yes, okay. And then top button, point it for a few seconds at the center of the screen.
Okay, and otherwise, okay, so thanks. Okay, good afternoon, everybody, and thank you for having me here. I'm a second year PhD student at the University of Geneva, and today I'm going to present you about my work about exploiting the sun as a star to improve the radial velocity technique as a whole for exoplanet detection. And in particular, I'm going to present a data-driven correction at the spectral level to improve the final radial velocity precision. So let's start with like a small overview about why we care so much about extreme precision in radial velocities. One of the future goals of our community will be to characterize the atmosphere of Earth-like planets, especially through space missions in reflected light. And of course, the more candidates we will have for these space missions, the more efficiently they will operate, which means that another important goal is actually the discovery of as many Earth analogs as possible, and possibly close enough to us for these space mission to actually see them. And for this reason, this last constraint makes the radial velocity series, the radial velocity technique the most promising one to our purposes,
sorry.
Which...
Nobody online can hear you. Can you get closer to the microphone?
Oh, I'm sorry. I'm sorry. So, okay. So, which means that we really have to improve the precision and the knowledge that we have about radial velocities to get down to this 10 centimeters per second that we need to detect Earth-like exoplanets, as was said already in the past presentation. To do this, we really have to deal with stellar effect and instrumental effect at the spectral level that vary the planetary signal. And just before diving into this kind of correction, I wanted to quickly have an overview about the radial velocity technique, because as we all know that we compute radial velocities using the Doppler effect, and we normally do it with cross-correlation functions, which means that we cross-correlate the spectra with a Mascov stellar line, we get an average line profile, and from this we get a radial velocity value. But 3CF, even though they are very powerful as a tool, they come with a loss of information, because all the wavelength-dependent features that we have, they might be averaged out during this process. And therefore, we end up losing some information that is actually precious if we want to go to a very high precision. A solution has been proposed to this, and it is to go at the spectral level and measure there the Doppler effect, the Doppler shift, and the radial velocity. And this is like called line-by-line radial velocity, and this is what I actually use for my work. The problem here is that we need some high fidelity spectra, which means that we need to correct at the spectral level for all the spurious signals that we know that are there that can vary the planetary signal before actually computing radial velocities. And we can do this, fortunately for us, using sun as a star data, and that can help us tackling this challenge of correcting the spectra at the spectral level. So this is the kind of data that I've been working on. I've been looking at 8 years of Arsenal solar data that you see here. Each point here is a radial velocity measurement, and you also have overplotted the 10 centimeters per second signal of a Earth-like planet orbiting a solar-type star. You see that the RMS of the radial velocity is much larger than this 10 centimeters per second signal. We would need to decrease it by a factor, more than a factor 10. And let's say, this is what we have in the radial velocity space. If we go back at the spectral level, we have something like this. After binning all the observation we had for HARPS, we get more than 2,000 spectra of this kind over 8 years, as represented in this matrix here. So here, each line is a residual spectrum with respect to a master stellar spectrum. while each column is what I call a spectral time series. So it's a flux as a function at a given wavelength bin as a function of time. And of course, the same jitter that we saw before in the radial velocity series is also present at the spectral level. So what we really need to do at first is to correct for all the signals that we know are there in the spectra, again, at the spectral level. This can be done, for example, with a pipeline called Yarara, which combines some data-driven and physical-driven methods to correct for tellurics, cosmics, then instrumental effects, and also stellar activity. I won't go much into details here, but you see basically that the correction works pretty well, and that the spectra after Yarara connection have a much smaller variability in flux. And this is much smaller variability also relates to a smaller jitter in the radial velocity. So the first map is what is associated with the radial velocity that I showed you before, while the question is how do we, what do we get if we use Yarara-corrected spectra? Well, this is what we get if we use Yarara-corrected spectra. You see that the magnetic circle is gone, that we have a RMS of the radial velocity below the 1 meter per second, yet this is not good enough to detect Earth-like exoplanets. And in particular, we see some substructures here that we can also see if you look carefully enough at the spectral level. So here is basically when my work starts, the core of my work starts, because we do see some residual signals in the Yarara-corrected spectra, and I wanted to try and correct for them further. So I performed a periodogram analysis of all the columns in this matrix, just to see how the spectral time series look like after Yarara correction. The output of this is that there are some persistent significant signal at the sun rotation at 1 year and also at very long periods. And, well, okay, the sun rotation is a clear stellar origin, which means that Yarara doesn't correct 100% for for the stellar activity. Then the early signal is likely instrumental and origin plus tellurics, while this long-term trend, they might be related to instrumental effects, but also some residual activity. And what I did as second step was really to try and fit a model, a simple model of these three signals to the spectral time series and then correct for them, just to see if they improve, if this correction improves somehow the radial velocity in the end. So if these signals that we still see have an impact, an actual impact on the radial velocity in the end. The answer is yes, even though we only have a 10% improvement in the RV RMS, and this is clearly, again, not enough. But this result suggested me that, like, three main things. So first of all, we do have some residual signal at the spectral level. This signal have a clear physical origin, but yet a linear model is clearly not enough to catch them entirely, which is why I moved on with my analysis using a PCA approach that I will try to summarize very quickly here. So first of all, let's go back to the Yarara-corrected spectra. And the first thing to do is to reduce the dimensionality of the matrix that we want to use for the PCA. So let's forget about the physics for a while. And then, as we don't really know what the PCA is going to do, which kind of signal it's going to detect, well, I really wanted to select only the column where I know that there is a significant signal. So I used the output from the periodogram analysis to do this selection, and eventually I ended up with a matrix of 2K per 40K by 40K pixel, on which I could run the PCA and extract some principal components that basically reproduce the residual spectra as a function of wavelength. Then we want to understand which of these principal components are actually important and significant in the PCA model. And to do this, I did a cross-validation test, which led to 16 significant components in the PCA model. I won't go into details for this, but I just wanted to show you some of these components, how they look like, just to show that they do catch some physical signals, like, for example, at 1 year and at longer periods. It's not just fitting noise. And this convinced me that, again, the model is working fine, and therefore I could correct for it my spectra. And you see that the actually PCA-corrected spectra show a much smaller variability, again, in flux. And most importantly, if we go at the radial velocity level, well, you see that if we compute radial velocity after the PCA correction, we really get to a precision of 40 centimeter per second. 40 centimeter per second with an improvement that can be quantified in minus 60% of the radial velocity RMS. And well, I must say that this result, I'm really happy about it, and because somehow it shows that we are going in the right direction to actually arrive to this 10 centimeter per second signal that we want, to the precision that we want to reach to detect Earth-like signal. But of course, like we have been taught that like such a good result cannot be also real unless we do some injection recovery test and we actually understand if the PCA is not just correcting and fitting for everything and perhaps absorbing the planetary signal. Well, I did this kind of test to understand how much the PCA improve in terms of detection limit that we can reach. Here you have the matrix of injected planetary signal at the spectral level. So again, we are reproducing the real case of an exoplanet around another star by injecting the planet at the spectral level. And in orange, you have the detection, the planetary signal that I could recover before the PCA correction. While here you have the planetary signal that I could recover after PCA correction. And just as a note, the PCA is runs from the beginning every time that I inject a planet. So like, if the PCA would absorb the planet, then we wouldn't get such a good improvement in detection medium. But well, actually, how good it is, this is my final result. You have the minimum mass that we can detect after the PCA correction as a function of orbital period of the planet that I injected, also color-coded with the gain that we have in detection limit with respect to uncorrected PCA uncorrected spectra. And well, the improvement is quite good, it's 30 to 60%. And again, I believe this result is very key because it shows us that the PCA is a good approach to get the best that we can after some physical-driven correction and push down the limit of exoplanet detection. And I will finish here, leave up my take-home messages, and I'm happy to take questions.
Thank you so much, Sarah. All right, questions for Sarah? Thank you.
Physically, I mean, well, not physically, why doesn't the PCA take out the planetary signal? Because naively, I would think it would.
Yes, well, the nice thing of working at the spectral level is that in principle, the flux variation induced by a planet on a planet is really, really tiny. So in principle, and this is what we weren't sure about before doing actually this sort of test. In principle, you are not able to see this small variation just because it's so tiny with respect to any other perturbation of, I don't know, stellar signal, for example. And well, I mean, we weren't sure this would be actually the case, but it seems to be the case. And indeed, the PCA doesn't see somehow the planetary signal at the spectral level.
Jen? Yeah.
Hi, Sarah. Excellent talk, Jennifer Burt. So your PCA is now, as you say, you're hitting your long-term and kind of yearly signals. YARAR is doing a better job with the short-term systematics and magnetic things. Are there timescales that you're still particularly worried about, either instrument or stellar variability signals showing up on that you think are making it harder to find planets?
Well, I must say this is the grid of injected spectra. I don't cover indeed yet that gap in between, I don't know, 30 centimeters per second and 40 centimeters per second. I would like to investigate that further, especially because before PCA, we do see that there are some, we are somehow biased. I don't know if 31 would be a detection, let's say. So I expect all the periods around the Earth revolution period being problematic, of course. But it doesn't seem to be the case too much after PCA correction, you know. So I'm positive about this not being a huge issue, but of course I need to investigate it a bit further for the early, around 1 year, let's say.